All right, in this video, I want to walk through 4 of the problems on the assignment that you're picking up here, entitled ICE Problems. A couple things I want you to note. First of all, if you wouldn't mind, make sure go down to number 7 and just cross out number 7. We're not going to do number 7. I'm not going to ask you to cover a problem like number 7. It's a little bit more elaborate than the ones that you're going to be responsible for. So right off the top, skip number 7, cross it out with malice if you wish. You will not have to do that problem. In the meantime, I'll point out these ICE problems. I actually have kind of come a little bit more accustomed to calling them RICE problems. And the reason that we call them that is because of an acronym, RICE, RICE, that we use to solve these problems. And you'll see that in the very first one, kind of what those stand, or rather the second problem, what those stand for. And it's a handy tool to organize information regarding reactions and equilibrium and things that happen as reactions proceed. So hopefully it'll be a helpful tool for you. I use it in chemistry, I use it in AP chemistry. Teachers and students all over the world use it. So it's a really important little tool to get used to using, and I think you'll understand it rather simply. The first thing here, number 1, is just kind of a problem to kind of remind you if you need to be reminded about how we set up K-Q problems. First of all, remember that a problem, they need to be balanced equations because those coefficients become part of the expression. For this problem, we're already at equilibrium. So the question starts out at the equilibrium point. This is like the problems that we've been doing up to this point. And so you don't have to do anything too special with this or anything different than what you've been doing so far. It'll be the next few questions in the video that will be a little different from what you're used to. So in solving for KEQ, we'll need products over reactants. Remember, that's always products from the right-hand side on the top in concentration mode, so with the brackets for each of them. And then the reactants here on the left-hand side go on the bottom of the denominator of your expression. And the powers of 1s here become powers of 1s on our brackets. Now, you don't necessarily have to write in powers of 1s, they're sort of implied, but that's where those coefficients will go on more elaborate equations. KEQ here then, if we know the concentrations for all 3 of these, we just plug them in, and we do. PCl3 is given in the problem as 0.15, and remember that's moles per liter or molarity. Chlorine is given as 0.37 moles per liter, and PCl5 is given as 0.010 moles per liter. We plug that in our calculator, calculate it out, we get an answer of 5.55. That's our KEQ value. That value at this point, again, is a ratio of products over reactants, and it doesn't have any units, it's just a ratio. So that's kind of where this question will end, and that's our answer. We determine KEQ, and we're all done. So that's just like the problems that we've been doing. So what I want to do is show you a few problems in here that are slightly different than the problems that you've been doing. And I'm going to jump down just to kind of start out here with question number 4. So I'd ask you to kind of go along to number 4 here as well. What makes this different is that the problem is kind of going to offer a sort of a before and after scenario. And you'll read it as you read these questions. There are a couple of others in this packet that are given to you at equilibrium, like number 1, but most of them involve a before and after scenario. First of all, we'll make sure that we balance the equation. Well, lo and behold, this is the same equation we just had. So we're going to use that same equation again, and we'll use the same KEQ expression again as well. However, there's a little difference in this one. It's telling us that at the beginning of this problem, a 1.10 moles per liter sample of PCl5 was placed into a vessel. Period. That's it. And then it says at equilibrium, it was determined that PCl5 was 0.33. So we have originally a concentration of 1.0, and at the end, a concentration of 0.33. So the concentration changed. And the reason that happens is, if we think about it, at the beginning, if they only put PCl5 into the vessel, right, then there's nothing else in there. There can't be a reaction in the reverse. There can only be a reaction in the forward. If we don't have all 3 compounds or substances in the vessel, we aren't at equilibrium. So these stories will start out, these ones that have a before and after component to them, they will start out with the idea that you're putting something into a container, but not everything into a container. So I'll help you to organize that here. In our equation here, our reaction equation, we're going to organize with that equation and below it our RICE table. So the acronym again, RICE. This stands for the reaction, or the ratios, sometimes we call that. The I stands for the initial, the C stands for the change, and the E stands for equilibrium. And each of these rows, initial, change, and equilibrium, is a molarity, a concentration or a molarity, moles per liter for the substance in that row. And so under each of them, it's basically that we're making a little spreadsheet. Under each of these 3 components of the reaction, PCl5 PCl3 and Cl2 will have initial, change, and equilibrium amounts for each of those three. All they tell us at the beginning of this problem is that we're putting PCl5 right into the vessel. So at the beginning of this, we're putting in initially a molarity of 1.10 moles per liter of PCl5, and that's all. That's all that's put in there. So there isn't any PCl3, there isn't any chlorine. Those you should enter as zeros in your initial row of your table. So it's like the before, and then there's the after equilibrium has been reached. It tells us that at equilibrium it was determined, and when you see the word determined, that would mean measured. It was measured that at equilibrium the PCl5 concentration was 0.33 moles per liter. Well, what happened to make that change? Let's think about it. If we have in this reaction PCl5 at the beginning, and only PCl5, the forward reaction is the only reaction that can occur. So initially, and you can make a couple notes here as you go through this first problem, initially only the forward reaction is possible because we don't have the stuff that it takes for the reverse reaction to occur. We don't have PCl3, we don't have Cl2, so the reverse reaction can't happen. And so what will happen? The forward reaction will occur, the reverse reaction will not, at least initially. And what will happen? Well, the amounts of PCl3 and Cl2 start at 0 each. The only thing that can happen there is that they'll increase. They can only go up. You can't go any lower than 0. So they're going to increase by some amount. And if they increase, it's because the reaction is making them. This reaction is producing PCl3 and Cl2. And as that happens, the amount of PCl5 has to decrease, has to go down. So we can put into our change line that some things, in this case the PCl5, is decreasing, and then some things are increasing, both the PCl3 and Cl2. Imagine on these tables that we can kind of divide them into reactants and products, and everything on one side of the arrow, in this case the reactant side, has to do the same thing. So all the reactants in this case will decrease. The products on this right-hand side of that dashed divider have to do the same thing, and they have to do the opposite thing. They have to increase. So as reactants are used, we see that as a minus. Products are formed, we see that as a plus. So these signs hopefully at least make some sense. Now here's the idea. We need to fill in some numbers. So how much did the PCl5 decrease in this case? How much did the PCl5 decrease? Well, if I look at 1.10 and it ends at 0.33, I can figure out that it decreased by 0.77 moles per liter. Right? That's how much it had to have gone down. If that's the case, because this is a 1:1:1 ratio, however much this one decreases, the others will increase the same amount because they're 1:1:1. So this one will go up by the same 0.77 moles per liter. This one will also go up by the same 0.77 moles per liter. Notice there in this row, the reaction row, we have a 1:1:1 ratio. And in our change line, we now have a 1:1:1 ratio as well. It's 0.77 to 0.77 to 0.77. That's a 1:1:1 ratio. These two lines, our reaction line and our change line, the mole ratios need to mirror each other or echo each other. So whatever your balanced equation is will come through in the size of the values in your change line, 0.77 across the board, because it was 1 mole in our balanced equation for all substances. So that ratio is a really big deal. As I go to fill in my last row, all I have to do is take initial and change and put them together. So for PCl3, I started at 0. I'm increasing by 0.77. It will end at 0.77. 0 plus 0.77. And the same is true for chlorine. It'll be 0 plus 0.77. So my equilibrium line, my equilibrium concentrations, when equilibrium is reached, as the problem says, at equilibrium, okay, those are my concentrations. And those are what I'm going to use to calculate KEQ. These are always the ones we're going to use in our KEQ expression. Because remember, KEQ is an equilibrium expression. And just like before, and I'll rewrite it just for the purposes of having it here on this problem, we're going to use the same expression that we used a few minutes ago on the very first question of the packet. PCl3 times Cl2 over PCl5. Plug those values in, 0.77 for the PCl3, 0.77 for the chlorine, and 0.33 for the PCl5. And when you plug that into your calculator, you should get an answer of 1.80 at equilibrium. So there's our answer for number 4. There's a lot of pieces to these problems, but the information that's given will help us to fill in the rest of the table, and then the equilibrium concentrations that I circled here in this blue are the ones that we'll use to calculate our K value when it comes time to do equilibrium constant calculations at the end of the problem, as it was here. All right, let's take a look at number 2. Back up to problem number 2. Again, this problem sort of suggests the same thing. 0.6 moles of SO2 and 0.6 moles of O2 are placed into a 1 liter container and allowed to reach equilibrium. That's, again, implying sort of a before and after. Those moles were put into a 1 liter container, and then time passed. Okay? When you see "and allowed to reach equilibrium," that means time is passing. And then at equilibrium, they tell us, the concentration of SO3 at equilibrium is 0.25. So they're giving us some of the same information as before. Let's go ahead and fill in our rice table. It's my reaction. It's actually a balanced formula already. Initial, change, and equilibrium again. I'll put in my initial amounts here in red. So I have 0.6 moles of SO2 in a 1 liter container. Well, 0.6 moles over 1 liter, this isn't real hard mental math, 0.6, that's 0.6 moles per liter. So when you divide by 1 liter, it doesn't change the answer much, right? And so for SO2, 0.6 moles per liter, 0.600 moles per liter. For oxygen, also 0.600 moles per liter. That's what they put in the container at the beginning. They didn't put any SO3 in there, so that's going to start out as a 0. And again, I'm going to kind of mentally divide my table here. The reactants are on the left side of that divider, the products are on the right. What else did they tell me? They told me that the SO3 concentration at equilibrium is 0.250. So that's going to go down here at the bottom for SO3, 0.250 moles per liter. And that's all they tell us. Find the K. All right. Looking ahead for my KAQ expression, all right, my expression will be SO3 squared, on the bottom SO2 squared, and on the bottom oxygen. So there's my expression. I'm going to need from the E line all these values, and I don't have much from my E line yet, so we need to fill in the rest of this table. What happened as equilibrium was reached? Well, let's look back to our table again for just a moment and recognize here that if at the beginning there wasn't any SO3, there's 0 SO3 at the beginning, again, only the forward reaction can get going initially. Forward reaction will be possible to start with. And what's going to happen over time is, as like in the last one, the amount of SO3 has to increase with time. Because it starts as 0, it can't go any lower. So the amount of SO3 has to increase with time. The amount, if that increases, the amount of SO2 has to decrease, and the amount of O2 has to decrease. Because logically, to make SO3, which is increasing from 0, we have to use the other things. We have to use SO2 and oxygen. Now, how much will they go up, or how much did they go up? We know that SO3 started at 0 and ended at 0.250. So it must have gone up by 0.250. Kind of makes sense. So it increased by 0.250 moles per liter. And then importantly, we've got this ratio up here, where SO2 and SO3 both have 2's as their coefficient, which means their change will be the same amount in size. If SO3 went up by, say, 2 moles, SO2 would have had to go down by 2 moles because they have a 2-to-2 ratio. If SO3 went up by 5 moles, SO2 would have to go up by 5 moles. They're linked to each other by that 2-to-2 ratio. And so in this problem, if SO3 went up by 0.250 moles per liter, SO2 would have to go down by the same 0.250 moles per liter. Those two have to be tied to each other. This 2-to-1-to-2 ratio means that in this line, we have to see the same ratio, essentially. That these two components, SO2 and SO3, have to change by the same amount. They don't have to change with the same sign, but they have to change by the same amount. And then hopefully we can figure out that if those are a 2-to-1-to-2 ratio, the oxygen is going to change here by only half as much, right? If this changes by 2 units, this will change, but oxygen will change by only 1 unit. It'll change only half as much. And so it's not going to go down by 0.25, it's going to go down by half as much. And if you fill in that row right here in the change line, you should see the equivalent of a 2-to-1-to-2 ratio, 0.25, 0.125, and 0.25. Or if you like fractions, this is 1/4, 1/8, and 1/4, which is a 2-to-1-to-2 ratio. Hopefully that makes sense. That change line can be a little tricky at first. If we fill in our equilibrium line, we just put those first two lines together. So 0.6 minus 0.25 gives me a remaining amount of 0.350. And for oxygen, 0.6 minus 0.125 gives me a remaining amount of 0.475. So there's my bottom line, my equilibrium line. That's what I'm going to put into my K expression. That's going to be 0.250 squared over 0.350 squared times 0.475. Be careful that you substitute things into the right spaces. A lot of times the mistakes happen because we get two numbers switched around or something, and especially when you're squaring one but not the other, that'll mess you up. Okay. Our bottom line answer then, punched in my calculator, 1.07 for your final answer. Hopefully that one made sense. We're going to move on next to number 6. All right, on number 6, the question is just a little different. That's why I wanted you to see this one before we conclude the video here. The difference in number 6, at least at first, is pretty obvious. It gives us the KEQ value. So in the previous questions, we've been solving for it. And on this one, we're actually asked to use it, being given the KEQ value, to solve for something completely different. The setup is still going to be the same. We're still going to use a rice table because they tell us at the beginning that a couple things are in the container and a couple things are not. So I'm going to fill my rice table in. This is a 1-to-1-to-1-to-1 ratio. So our favorite kind of simple ratio for this problem as well. Makes that change line a lot simpler to navigate when everything's in ones. What are they telling me initially? A mixture of sulfur dioxide and nitrogen dioxide is prepared. Well, those are my reactants, so sulfur dioxide, nitrogen dioxide, each with an initial concentration. So there's that word, initial, right? So we're talking about the initial concentration of 0.10 moles per liter. So, oops, I'm going to go ahead and fill that in. 0.10 moles per liter for this and for this. 0.10 for both of my reactants. And that's all that's in there. That's the mixture. In other words, there's none of this nitrogen monoxide, there's none of this sulfur trioxide. As with the others, and I think all of the problems on this packet pretty much start out with a situation that's pretty simple like this, where there's some reactants and there aren't any products. So as before, the forward reaction is the only one that will happen to start, and as this reaction occurs, as the reaction reaches equilibrium, the reactants will have to decrease because they're going to be used up. So both of these will go down because they're going to be used. And the reason that we know that is because the products have to go up. They start at 0, they have to increase because they can't go any lower than 0. So how much are they changing? Let's see what else they told us. Calculate the equilibrium concentrations. Let's see, they're asking us to calculate the equilibrium concentrations of nitrogen dioxide. So they want this value that's going to be on this spot, and of nitrogen monoxide. So they want the value that's going to be in this spot. And that's all they tell us. So, wow, that's not very much information, at least it seems at first. But look what we know here to fill this in. Because we know that these two products on the right will have to both increase. Okay? We know they go up, so we have positives filled in on our change line. But how much will they go up? We don't know yet. We just know that they're going to go up by the same amount, right? Because they're a 1-to-1 ratio, they're going to go up by the same amount. They're going to go up by X. And since this whole reaction is a 1-to-1-to-1-to-1 ratio, right, from that top line, they need to match up. We know that if these go up by X as products, then the two reactants will have to go down by X too. So if I imagine there, in front of these, there's a 1 in front of each of those, right? 1-to-1-to-1-to-1 matches up with the coefficients of 1-to-1-to-1-to-1. They're going to change by some equal amount. It's just that the two reactants will decrease by that amount and the two reactants will increase by that amount. So that ratio should be carried through on that change line. That's such an important part of this. So what does that give me for my bottom line? Well, this will be 0.100 minus X. This will be 0.100 minus X. This will be 0 plus X. So that's just X. This will be just X as well. Now, that's not an answer, right? We don't have an answer for those two blue boxes yet, but we need to get one. So let's step back again as usual to the KEQ expression. What will our KEQ expression be? Well, it's going to be NO on the top and SO3 on the top, both to the first power, SO2 and NO2 on the bottom as reactants, both to the first power. That's my expression. The line's a little big. Shrink that down. What do I know with that? Well, I know the KEQ value. So that's 85. That was given at the top of the problem. So that KEQ value was given as 85. The other things you might say, well, I don't know anything else. Well, it's true and it's not. We can fill this in. Even though we don't know those values, we can fill them in. So on the top, I'll have, for NO, I'll have X. And for SO3, I'll have X. So we have X times X. On the bottom, I have 0.100 minus X for both of those terms. So 0.100 minus X and 0.100 minus X. Now, if you're math savvy, or even if you're mildly math familiar, you probably recognize that we have on the top X times X, which we can simply write as X squared, right? So I'm going to go ahead and do that. Let's just call that X squared. And on the bottom, I have 0.100 minus X squared. So again, I'm going to clean that up just to kind of shorten things. I'm going to call that what it is, and that's that. Why does that help me? Well, if at this point you're looking at it and saying, well, how do I solve it from here? you might be afraid of the fact that in the bottom you'd have to FOIL this out. And when you have to FOIL things from your old math days, people start twitching inside, and they don't even know why. But if you're looking at this with a different eye, you might recognize that there's another alternative, right? And that alternative is to use the square root of both sides. Because if I find the square root of both sides, I'll get rid of all those nasty squares, and I'll have a lot easier time of it from there, because without the squares, the math is much, much simpler. So square root of 85 in my calculator gives me 9.22. All right. On the other side, if I do the square root, on my numerator, I'll have the square root of x squared, which is just x. And in the bottom, I'll have the square root of 0.100 minus x quantity squared, which is 0.100 minus x. That's a lot easier than what we had, I think, right? So as we go to solve it from here, it's really just a matter of cross-multiplying and dividing and kind of solving for x. Now, I'll work out the algebra with you on this one because I know a lot of people are a little less than comfortable on these the first time through. Some of you aren't real math fans, but let's work it out. So we'll cross-multiply first. So across the side here, I'd have 1 times x, so that's x. And as I cross multiply here, I'll have to distribute 9.22 into that term. So on the other side of the equivalence equal sign, I'll have 9.22 times 0.1, which is 0.922. And I'll have 9.22 times negative x, so minus 9.22x. Group-like terms, I'm going to add to both sides 9.22x to get those x's together. And that'll give me 10.22x equals 0.922. All right. Divide both sides by 10.22 to get the x by itself. And 0.922. 0.922 divided by 10.22 gives me an x of 0.0902. And that x then is what? Okay. In math, we often might stop and say, okay, I got it. I've got x. Well, what is x? Well, look, up here in the box, x was the NO concentration. So one of the things they wanted me to find is found. The NO concentration at equilibrium, which in my Rice table was simply x, is then 0.0902 moles per liter. But the other thing they wanted for me was this. They wanted the NO2 concentration. And so the NO2 concentration isn't just x. It's 0.1 minus x. So it's going to be 0.100 minus 0.0902. And that then is 0.00998 moles per liter. So that's my NO2 concentration. Okay. There's one of my answers. Whoops, there's one of my answers, and there's the other one of my answers. So this Rice table is very similar to fill in as compared to the others. The difference was at the end that we weren't solving for k, which is kind of the simplest way to go, which you just have to punch numbers in and go. In this case, we were given k and had to solve for something else, but it's all just about organizing a k expression. It's all about arranging a Rice table based on change, and the key line here is really recognizing, I think, that there's that common ratio from the reaction equations coefficients of, in this case, 1 to 1 to 1 to 1, to the change line, which also has to resemble or mirror that same ratio. And then keeping in mind that we can sort of divide the Rice table in half, and that things on one side of that divider will change in the downward direction, and things on the other side will change in the upward direction, or vice versa. There's actually scenarios where it goes the other way too, but things on one side have to do the same thing, which would be decrease or increase. Hopefully that makes sense to you. The rest of the problems in this packet are very much like those. There actually are a couple in here that are just like number 1, where you just have to do equilibrium calculations because you're given equilibrium amounts. I believe it's number 8 and number 9 that are just like number 1. So those are a little simpler. You shouldn't have to use a big Rice table for 8 and for 9. But the rest of the problems on this assignment are just like the ones we've done here on the other examples, 2, 4, and 6. Using a Rice table, filling it in from what you're given. And then again, remember to skip number 7, because that's a big, ugly kind of problem whose math we aren't going to hold you responsible to know. Hopefully that helps. Try as many of the other ones as you can. If you're in class, work on them together. Make the most of that time. Troubleshoot with each other. And I'll see you when I see you. Thanks for the work. Talk to you later.